Okay, well, let's finish up our summary lecture of machine learning as we're trying to pull this all together, thinking about the applications of machine learning. We talked about various types of things that where we can be using this. And now we finish up with a short discussion on principal component analysis. The potential problems with data are noise and redundancy. Covariance matrix describes all the relationships between parts of attributes in our data set. To reduce redundancy, ensure each variable covaries as little as possible with other variables. In an optimized matrix, all off-diagonal terms in sigma are zero. And remember, this is a matrix that we have considered previously, and you'll see it again here. Note that removing redundancy diagonalizes sigma. We can visualize the data with n attributes x1 through xn as a cloud of endpoints in a n-dimensional vector space. The n by n matrix X is given as such as we're listing here. When we subtract the mean from each of the data dimensions, we get the transformed data in mean deviation form. For principal component analysis, working with the data whose mean is zero is more convenient. From now onward, assume that the given data set is a zero mean data set. Xi still represents for the zero mean data set as well. For this data set, we have this equation for sigma x. In terms of x hat, the covariance is given here by this equation. Thus, the symmetric covariance matrix sigma x hat can be diagonalized by selecting the transformation matrix W to be a matrix where each row is an eigenvector sigma x hat. By the selection here, W equals to ET, this was the first goal for principal component analysis. The next goal is for reducing noise. We see here that sigma z hat is equal to ET, sigma x hat E is equal to the delta. The variance in the transformation domain are therefore given here, and so we have this type of way of formulating that information. So that gets into the math. So sorry to have to dig through that, but here we have our last slide for summarizing the principal component analysis. The largest eigenvalues thus correspond to the maximum variance. Therefore, the first principal component is the eigenvector of the covariance matrix sigma x hat associated with the largest eigenvalue. Other principal components are given by eigenvectors associated with the eigenvalues with decreasing magnitude. The next step is to order the eigenvalue-eigenvector pairs by the magnitude of their eigenvalues in descending order, selecting the leading k components that explain more that, for example, 90% of the variance. The final step in principal component analysis is to derive the new data set transformation of the original data set. So ultimately, you're trying to get it down to just a few factors that can carry the bulk of what you are trying to analyze. And so then you just focus on that. And so thus you have the principal component that is the most important thing for you to consider. All right, well, thank you very much. That's going to end this lecture, and that's the last for this class. So I hope you enjoyed it. It's been a pleasure to spend this time together with you. God bless.